Clustering is a process of grouping data based on similarity. Clustering results depend on many factors, including the choice of algorithm, parameters, and the choice of a similarity metric. No clustering algorithm is perfect. In this example, the algorithms didn't find the appropriate number of clusters. We explore different algorithms which produce better results, yet we still have a couple of points that are ambiguous. In this video, we introduce methods to compare clusterings, to visualize cluster fit, to refine cluster assignments, and to judge clusterings based on contextual data. We integrate our techniques with Caleydo StrataMax. StrataMax is a web-based visual analysis tool targeting biomolecular data, which is also well suited to compare clusterings. It visualizes stratifications of patients based on clusterings of data matrices. Each dataset is shown as a column. Groups of patients are shown as blocks in a column. The relationships to groups in other columns is shown by ribbons. The thickness of the ribbons indicates the number of patients shared among two groups. We introduce improvements to StrataMax which can be used to evaluate clusters, to refine clusters, and to visualize the results of fuzzy clustering algorithms. In our workflow, users first create new clusters by running clustering algorithms with a selection of parameters and similarity metrics on a dataset. Next, investigators visually explore the quality of cluster assignments and compare it to other clustering results. Based on the visual exploration, they can manually refine and improve cluster confidence while examining the new results instantly. When a satisfying clustering result is found, analysts can interpret the result. We will now walk you through these steps in our system. We start by running a clustering algorithm with full control over its parameterization. Here we choose k-means with 3 clusters and use Euclidean distance as the similarity measure. The clustering result is shown as a new column in StrataMax. We can repeat this process and choose a hierarchical clustering algorithm to compare it to the k-means result. For hierarchical clustering, we can change the number of clusters dynamically. After the cluster creation, we can visually explore the cluster results and evaluate cluster assignments. We can start by sorting the records in a cluster by the distance to the cluster centroid, which we also visualize as bar charts next to the heat map. This view shows both individual distances and the overall quality of the cluster. We can also explore the distances of a record in a cluster to all other clusters. We see a matrix of bar charts where the columns correspond to the clusters. That means the first column shows the distances of the records to the first cluster. The second shows the distances to the second cluster, and so on. We can sort the data by each of these columns. This view allows analysts to judge whether a record would be a better fit for other clusters. For cases with many clusters, we can also visualize this data as a grayscale heat map. We can refine clusters based on the information of the distance views. They provide sliders dividing the clusters into 3 different regions: those that fit well, those that fit okay, and those that only fit poorly. We can refine these thresholds independently. Once we found good thresholds, we can split the cluster. The new clusters are shown in a new column. We can now add another dataset and apply the split to it. Here we show a Kaplan-Meier plot that visualizes patient survival for these clusters. This allows us to evaluate whether there is a clinical effect of this refinement. We can still update the thresholds after the splits, which also is applied to the Kaplan-Meier plots. Once we are confident about the results, we can integrate the split back into the original column. In addition to splitting, we can also merge clusters. These clusters here look similar, so we'll merge them. We have arrived at an improved clustering. we can see that the patterns in the clusters are consistent and that the survival curves for the clusters are quite different. Our methods also work for fuzzy clustering. When we use a fuzzy clustering algorithms, patients can belong to more than one clusters. Instead of distances, we show probabilities of each element belonging to one cluster for fuzzy clustering. Fuzzy clustering uses a threshold to decide whether an element is unique to a cluster or belongs to multiple clusters. Here, green bars indicate that the record is unique to the clusters, whereas purple bars show that the same record is also part of other clusters. This completes the tour of our cluster assignment analysis and evaluation in StrataMax. Thank you for watching our video.